Hello, everyone. Today we're going to start with Chapter 9, Section 3, which is Solid Hydrates, which is on page 259. But before we get into this, I just wanted to say that on the homework, I had messed up. The correct answer was C and D. So I know two of you had submitted it before I changed the answer. You will get full credit for that, so I just wanted to tell you that. So we're going to get started with Section 9.3. which is solid hydrates. So, some ionic compounds attract water strongly enough to hold onto water molecules even when crystalline, forming what they are called solid hydrates. So, we are going to define solid hydrates, which is when ionic compounds attract water strongly enough to hold onto water molecules. Okay, so for example, the plaster of Paris used to make decorative objects and casts from broken limbs is calcium sulfite hemihydrate, which is written like so. It's going to be written like CaSO4, which is the calcium sulfate hemihydrate, and this is going to be the hemihydrate. So the dot between here indicates that for every 2 CaSO4 formula units in the crystal, there is also 1 water present. So, after being ground up and mixed with water to make plaster, this gradually changes into crystalline dihydrate, known as gypsum. So, during the change, the plaster hardens and expands in volume, causing it to fill and mold or shape itself closely around a broken limb. Table 9.3 on the next page lists some of the other ionic compounds that are handled primarily as hydrates. Still, other ionic compounds attract water so strongly that they pull water vapor from humid air to become hydrated. Compounds that show this behavior, such as calcium chloride, are called hygroscopic. So that's going to be our next definition, which is hygroscopic, which is having the ability to pull water molecules from the surrounding atmosphere. And these are often used as drying agents. You might have noticed a small bag of hygroscopic compound, probably silica gel, SiO2, included in the packing of materials of a new MP3 player, camera, or other electronic device. So for example, I got my document camera, came in this little box here. So this little packet right here, this contains active carbon, which is the drying agent so that this doesn't get wet per se. And that just keeps things fresh. And it's to keep humidity low during shipping. So the next thing that you guys need to know from this section is going to be this table in your book right here, which is going to give you the common solid hydrates, their formula, the name, and their uses. So if you guys will pause the video right now and check this out and copy this down in your notes, that'll be a great idea. For example, I could ask you any question like, what's the name of the common solid hydrate used for casts and molds? And you would say calcium sulfate hemihydrate. And then, or I could ask you to pick out the correct formula for one of these as well. So that is going to be 9.3. So the next section, since that was a quick section, we're going to do 2 today. We are going to do 9.4, which is going to be solubility. And this is going to be on page 260 of your book. And your homework for the 9.3 and 9.4 section are just going to be questions on Google Forms, which is in RedWeb. There's only a couple questions about these 2 sections, but since there isn't very many problems in the book, I added a couple of my own, and those are the ones that you guys are going to be held accountable for. So let's get to work with 9.4, solubility. We saw in section 9.2 that ethyl alcohol is soluble in water because hydrogen bonding is nearly as strong between water and ethyl alcohol molecules as it is between water molecules alone or ethyl alcohol molecules alone. So similar are the forces in this particular case. In fact, that the 2 liquids are miscible or mutually soluble in all proportions. Ethyl alcohol will continue to dissolve in water no matter how much is added. So the first thing we're going to define is miscible. And miscible, like we just stated, is it's mutually soluble in all proportions. So what does that mean? That means that it will continually dissolve no matter how much is added. So it will dissolve continuously. So most substances, however, reach a solubility limit beyond which no more will dissolve in a solution. Imagine, for instance, that you are asked to prepare a saline solution. You might measure out some water, add solid NaCl, and stir the mixture. Dissolution occurs rapidly at first, but then slows down as more and more NaCl is added. Eventually, dissolution stops because an equilibrium is reached when the number of sodium and chlorine ions leaving a crystal and going into the solution are equal to the number of ions returning from the solution to the crystal. At this point, the solution is said to be saturated. So the next thing we are going to find is saturated solution. So a saturated solution is a solution that contains the maximum amount of dissolved solute at equilibrium. So the equilibrium reached by a saturated solution is like the equilibrium reached by a reversible reaction. Both are dynamic situations in which no apparent change occurs because the rates of forward and backward process are equal. Solute particles leave the solid surface and re-enter the solid from solution at the same time. So this can be written as a solid solute can dissolve into a solution, or a solution can crystallize into a solid solute. So this is reversible. The maximum amount of substrate that will dissolve in a given amount of solvent at a given temperature, usually expressed in grams per 100 milliliters, is called a substance solubility. So the next thing we are going to define is solubility, which is the maximum amount of a substance that will dissolve in a given amount of solvent at a specific temperature. So, like I said earlier, how we usually write this is going to be, it's expressed in grams per 100 milliliters. So, solubility is a characteristic property of a specific solvent combination, and different substances will have greatly differing solubility. Only 9.6 grams of sodium hydrogen carbonate will dissolve in 100 milliliters of water at 20 degrees Celsius, for instance, but 204 grams of sucrose will dissolve under the same conditions. So it's always different. We are going to discuss the effect of temperature on solubility and how that can change it tomorrow, which is going to be chapter 9, section 5. But for now, this is all we're going to do today. Please do your homework on RenWeb. And then if you guys have any other questions, please feel free to reach out for me or write down your questions so that I can answer them during our Zoom conference on Thursday.